Okay, let's talk about Pascal's triangle. So how do we start? Well, we can start by building a little foundation. So you kind of have this small little triangle. We can keep adding ones on the outside. And then how we find the values inside is by adding the two ones. And so forth. So 1 plus 2 is 3. 1 plus 2 is 3. Then we have 4. 3 plus 3, 6. 4. Let's continue the trend up until 7. So you can understand the pattern. So we have 5. 4 plus 1 plus 4. Then we have 10. 10 and 5. Let's continue. Okay, well, what is 1 plus 5? Well, that's 6. 15. 15. Oh, excuse me, 20. But poor mathematics. 15. And then we have 6. What exactly is this Pascal's triangle? Well, when we want to solve binomial expansion questions, so something... Let's start off with an easy example. Raised to the second power. If we want to solve this using the known method, we can say, well, this is x plus 2, x plus 2, and we can use the distributive property, or we can use the FOIL method. X times x, x squared, x times 2, 2x, 2 times x, 2x, and then 2 times 2 is 4. So we can add the like terms. That gives me 4x plus 4. Now, when we see this value in Pascal's or in a binomial question, we can actually go look at, we can think about this as the rows number. Okay? The rows number. So in this case, we're looking at the second row. Now keep in mind that when we use Pascal's triangle, we start counting from 0, not 1. This is very, very important. I'm going to make it MB. Very important. Right? So 0, 1, 2. So this will be our second row. So let's go see how this works. Well, the technique I'm going to use is I'm going to create 3 brackets for each number in the triangle. So that gives me 3, 6, 9. So let's expand. So let's say 1 plus 1 plus another group of brackets. So what exactly goes in the first bracket? On the first bracket we can insert the Pascal value of the triangle. In the second bracket I can insert my first term. So I'll insert my first term, and then for my final bracket, my third bracket, I will insert my second term. Does that make sense? I hope so. So let's insert. Okay, so we said our Pascal values. We find 1, 2, and 1. Now I'm going to insert my x's. X, x, x. And I will finalize with my 2, 2, and 2. Now here's the technique you need to use. We can start off by saying we want to go from, when we work with our variables, we want to start at our highest variable and move all the way to our lowest variable. When we go to our second term, in the second bracket, so I'm referring to this one, we want to go from 0 all the way to 2. So let's see. So 2, 1, 0. And then I have 0, 1, 2. How I can identify this is by adding, if I add my two values from my exponents together, it should give me my original exponent. So 1 plus 1 is equal to 2. That makes perfect sense. Now let's solve this one. I'm going to solve this one down here. 1 I will cancel out because nothing happens to it. Anything to the power of 0, let's make a little note here. a to the power of 0 is equal to 1. This is an exponential rule. Something you need to know when solving these binomial expansion questions. I'm going to cancel out these two. The same thing happens here. X to the power of 0 is 1. And I'm going to cancel out this one too. So now let's multiply. I'm left with x squared plus 2 times x is 4x. And then 2 to the power of 2 is 4. And if we notice that while this answer is exactly the same as this one, do we see the connection? Now let's look at another one. Let's look at some basic combinations. So how do we solve combinations? Well, combinations means if I have, let's say I have 6 students and I want to pick 2 of the students, how many pairs can I make? So 6, choose 2. This is how it would look. Now for combinations we have a formula. That formula is n factorial over r factorial multiply n minus r factorial. So what exactly is factorial? Oh, there's many things we need to keep in mind. So factorial means if I have 5 factorial, or this exclamation mark, we can say, well, this is 1 times 2 times 3 times 4 times 5, which is equal to 120. Now, how do we use this in our combinations? Well, let's go a bit down. Okay, let's go a bit down. So I'm going to write C 6 because I have 6 total students to choose from and I only need to pick 2. Let's go insert our values. We have 6 factorial over r, which is 2 factorial, multiply n, which is 6 minus 2, that gives me 4 factorial. Now I can actually simplify this. Well, I can say 6 times 5 times 4 factorial over 2 factorial multiply 4 factorial. And since we have multiplication, we can simply cancel these two out. Since the numerator and the denominator is the same, we can cancel. That gives me 30 divided by 2, because 6 times 5 is 30, divided by 1 multiplied 2 is 2, which then gives me 15. Now let's take this 15. So there's 15 possible combinations that I can pick if I have a total of 6 students and I need to pick 2. Okay, so let's write here total students. Total students is 6 and I need to pick 2 of them. Now let's go back to our Pascal's triangle. Okay, so we know that the possible combinations is 15. So let's write that over here. So the possible combinations are 15. Now look at this. I can think about this as, or not think about it, I can now use actually Pascal's triangle to find my answer without calculations. Well, the 6 would be the row, and the 2 would be the number in the row. Number in the row. So if I have 6, choose 2, I can go down and find my 6th row, which is, I will use a sign, which is this. This row would be my 6th row. And remember what I said, we start counting at 0. So 0, 1, and 2. And if I look at this value, well, this seems to be the exact same value as 15. Now we can see how Pascal's triangle is used not only as a mathematical piece of art, but it can use to be solve binomial expansion questions, and it can also be used to solve combination questions. I'll make a bit more of a detail when it comes to the binomial theorem, however. I'll make a great detailed video. But I just wanted to show you the beauty of this beautiful triangle that we call Pascal's triangle. Now, to be fair, there were other civilizations that used it before Pascal. If I recall correctly, Pascal was in the 1600s CE, while Chinese mathematicians used it in 1200s, if I'm not mistaken. So is it really fair to call it the Pascal triangle? Well, we don't know. And that's a question I'll leave up for debate and for you to decide.